All right. Welcome to the end of week 2. A couple of announcements. Problem set 2 is available online in both standard and hacker edition. Do as before, choose which one suits you best. And another announcement as well. In response to popular request, we've decided to try offering the analog of super sections for those more comfortable, so to speak. So we posted an announcement about this on the bulletin board. Take a look for more details. But we will start the first of these this coming Monday, even though it is a holiday, at 7 p.m. Maxwell Dworkin room will be announced via the course's bulletin board by probably Sunday, certainly by Monday. The first is going to be led by Michael Tucker, one of the course's teaching fellows, who's an alumnus of the college, has been working for the past several years for a fairly sophisticated local software company that does very advanced search algorithms for large databases. The purpose of these hacker sections is not to be more advanced versions of the regularly scheduled sections. Rather, they're meant to supplement that same material. So the idea is that those of you who are more comfortable and more interested in pushing your knowledge beyond the scope of the course, learning techniques, learning tricks, learning just about cool stuff that's largely beyond the scope of, say, the week's problem set, might enjoy attending this optional hacker section once per week in addition, say, to your own section. So whereas the super section is meant to review much of the week's material, the hacker section will be meant to extend beyond the week's material. So any questions, do just let us know. But because for us this is very much an experiment, as I said in the bulletin board post, we do want your input, because we're only doing these because some of you seem to want them. So do let us know how we'd best direct them. 7 p.m. Monday, Maxwell Dworkin, room to be announced. Any questions before we forge ahead? Okay. Then I have a question for you. We've looked over the past few days at not only a bit of new syntax, but more about features of C and capabilities. What's a function in a sentence? What's that? Nothing. What's a function? What's a function? Yes? OK, sure. So it's like a miniature program that carries out some task. Functions, as you know, can have return values or they cannot. What does it mean if a function does have a return value? Yeah, so it outputs a number, or even not necessarily a number. It outputs, and even outputs might be misleading. It returns, quite literally, an int, a char. We'll see that you can return strings, or more properly, pointers to strings, and a whole bunch of other things. So it's a function in the sense that it takes input, and it does produce output, but that output can be retained, say by assigning it to some variable. What, though, is a side effect? If a function has a side effect, what do we mean by that? Subtler. Yeah? Good. So the task that the function performs doesn't necessarily involve returning a value, but it does have some effect. For instance, printf is a very nice example of a function with a side effect, because even though technically it takes inputs and it appears to produce output, but largely the output it produces is purely aesthetic. And the function, say main, that calls printf doesn't necessarily know what printf did with regard to your string, because it is in fact a side effect. It's not as though it's returning that string as a return value. So we concluded on Wednesday by looking at buggy6.c, and we took a look at what might happen if you iterate just a little too far when it comes to arrays. Sometimes if we iterated even further than, say, 1,000, we might, in fact, be able to induce a program to crash, though it does sometimes depend. So recall last time when we ran this program, and this was buggy6, lib CS50, and then ran this thing, and then I typed in 3 arbitrary scores. We got a whole bunch of junk in addition to the 3 scores that were echoed back. Well, let's just see if we can push our luck a little bit more and iterate not from 0 to 1,000, which already seemed problematic, but let's add a couple more zeros to that and see what happens this time. I'm going to recompile. I'm going to rerun a.out. And let's take a look what happens. Again, 3 arbitrary scores. So if you push your luck a little too far, you might actually induce a real problem, something that apparently is called a segmentation fault, core dumped. Okay, one of these messages that on first glance might not be all that helpful, but if I go ahead and type ls to look at the files in my directory, what might jump out at you now? Okay, so core. So this is a file, and let's actually type a command you've used at least once before, I believe, ls-l, which gives you the long output. And notice in the middle column here, core is pretty darn big, 300 kilobytes. And that's quite larger than, say, most of the other files in this directory. Well, we'll get to this more when we look at debugging techniques in this class. But I mention it now because even a couple of you have encountered these core files in your directories, be it for problem set 1 or perhaps coming up for problem set 2. The explanation? You screwed up. So there's a bug in your program, and your program dumped core. What this is going to mean for us is that what an operating system often does, if configured in this way, when something really bad happens, usually involving some memory-related mistake that you've made, it dumps core, which means it puts a file in your current directory that essentially contains the contents of RAM as they were when your program made that mistake. The idea being that by capturing the state of your program and saving it on disk, you, the developer, can go poking around inside of the memory and figure out what the bug might be. So we'll actually analyze these core dumps in the weeks to come when we look specifically at a debugger called GDB. So they're actually quite helpful. For now, they take up space. So do know if you do make this mistake and it has no value to you for now, rm core will save you the time from submitting a 300 kilobyte file along with your programs, which is obviously clearly an indication that even if your programs once submitted are correct, clearly you messed up along the way. So you can cover your tracks in that sense. So let's take a look now, again, at these things called arrays. So what, in a sentence, was an array? Yeah. All right, so it's a collection of variables. It's usually a collection of variables of an identical type. We looked, for instance, at an array of grades, which really meant what in terms of memory? What's an array? Someone must have. Yep. Yeah, so it's sort of a list of memory indexed by number. So it's a chunk of RAM that's reserved contiguously so. That is, every variable inside of it is going to be back to back to back to back, but you can randomly access elements in that array by way of their indices. So now a more important question. Who cares? Why is this useful? Tough crowd today. Who cares? Yes? Yeah, so it does let you store a lot of numbers or generally information at once, and in a way that's sort of dynamic. You don't have to know a priori necessarily how much space you're going to need. For instance, if you don't know how many grades or how many tests a student has taken, you don't want to hard code in 3 quizzes as your constant into your program, because then it's clearly not capable of scaling to more larger inputs. But if you instead ask the user how many quizzes did you take and then create an array, ideally we should be able to create or allocate just enough memory for how many quiz scores the student actually has. And so that's the spirit of these things. Let's take a look at string1.c though, because it turns out that we've been using arrays for quite some time, perhaps unbeknownst to you. So this program looks to be quite short. It first gets a line of text using getString, which is in CS50's library. It then checks this thing, if s not equal to null. So this is a habit you need to start getting into. Most functions that might run into a problem return not only just return values in the expect you would sense, but they often return error codes in some sense. GetString, it turns out, if you look closely at the CS50 library code, which we released last time, you don't have to look at it just yet, but if you do look closely, you'll see that if something goes wrong with regard to getting a string from the user, that function getString won't return a string, obviously, because something went wrong, but it will return some kind of error code. And that error code in this case is a special symbol called null, all caps N-U-L-L. And what it really just denotes is the number 0, which in this case happens to mean that getString didn't return a string, it's null. The problem is, though, if something goes wrong inside of functions like getString, and you don't check what the return value was, and you just assume that this worked, you might end up trying to access memory that is a string that isn't even there. And we've just seen an example of what happens if you take those leaps of faith without actually checking that the memory is yours. So henceforth, when you are using getString, the habit you should get into is check if its return value is null, and only if it's not, that is, only if a real string came back, should you proceed to do something with the string. Otherwise, presumably, you want to err and inform the user of a problem. You want to quit. You want to have them try again. It depends on the circumstances. But let's assume that the string did, in fact, come back. So s does not equal null. What am I doing in that inner loop? that for loop? I mean, a right answer here might be print string, 1 character per line, but how is that working? So we're iterating from I equals 0 to what? I mean, just infer from the syntax. Yeah, exactly. Exactly. And that's actually the revelation with this example, is that even though we've been treating strings as sort of a data type, that's actually been a bit of a white lie, because a string, as you know it in CS50's library, is really just a synonym for something called char star, which happens to mean a pointer to a char, but we're going to get to that in the future. But for now, string and char star are synonymous for reasons we'll see in a second. But it turns out strings are really underneath the hood, as you say, just an array of characters. So when you've been calling getString, and suppose I type in the word foo at the keyboard and hit enter, what the user's getting back conceptually is FOO, as you would expect. But what's really being returned, in a sense, is an array that is a contiguous chunk of memory of characters. This is index 0. This is index 3. And inside of this array is FOO. And then, it turns out, a fourth character always, \0 or null. So strings always have a representation in memory as an array. So FOO comes back to back to back in RAM. But the computer needs to somehow be able to know where these strings end. So the point of this thing, every string in C is quote unquote null terminated, means that by checking the last character in a contiguous block of characters, you can check, is this the end of the string? And if it's anything other than 0, or really \0, so we don't confuse it with the numeric value, well, then the string continues. So why is this useful? Well, in this case, I get 0, I is less than strlen, which means string length, of S. Well, take a guess. How does this function that apparently exists, called strlen, work? How does it figure out the length of a string? Yeah. Yeah, so it counts the number of letters in the string, probably by itself using some kind of for loop or a while loop and iterating from the start of the string again and again and again until it finds this null character, checking it presumably with some kind of condition. And then once it finds that null character, it returns the value of some variable like counter or I that was simply counting up the number of characters it had countered. Well, you don't have to implement strlen because this is one of the functions you get for free with C, much like printf. Someone else implemented this, but we can certainly use it. And then notice in the line beneath the start of this for loop, what's this blinking line here apparently doing? I mean, based on what you know already about arrays and just characters, yeah. Yeah. Exactly. So if an array looks like this, and we know how to access elements in an array, last time on Wednesday you simply said something like grades bracket I to get the ith grade in your grades array. Well, similarly, can we get the ith char from a string that is an array of characters just by using syntax like that on the blinking line? So I'm tucking away the ith character in S, in C, and then clearly I'm just printing it out followed by a new line. And before fielding a couple questions, let's just see the net effect of this code. So GCC of string1, libcs50, compile that, enter. All right, I'm going to type in my string, say foo, and what it does appear to do is print a character for character. Let's do something a little longer. Foo, bar, baz, borrowing the nomenclature of Wednesday, and similarly does that print character by character, line by line. Okay, a couple of questions here first.
When you have strlen in the condition part of the loop, does it get called every time with the loop?
Oh, that is the perfect setup question. Yes, in fact. So what's stupid about this design? Well, we'll recall this basic definition of a for loop. We said that the thing before the first semicolon were the initializations, then we had the conditions, then we talked about the body of the loop getting executed, and then what happens last? Just as a sanity check. The so-called updates, right? The thing at the very end of the for loop in parentheses. Well, it turns out that the conditions are executed every time the loop is executed. Otherwise, how would you know if maybe the condition is no longer true or false? Well, if you're calling a function inside of the conditions, the implication is that every time this loop iterates, you're calling strlen, strlen, strlen. Now, why is that stupid? Okay, so, well, strlen's constant, be more precise. Well, it's a waste of memory. It's more a waste of CPU cycles, right? Because if it's executing. So be more precise. What's stupid about this?
It doesn't change within the loop.
Yes. So S is not changing ever. And as such, its length is never changing. So why would you constantly check again and again and again and again if the length, if I is less than the length of some string, constantly recomputing the length of that string? So what would be the obvious sort of engineering solution here be conceptually? Also set a variable. So I say that was a perfect setup because it just so happens in string2.c we have this enhancement. And we said that for loops can have in the plural updates and initializations and conditions. Well, you simply separate them as promised with commas. So what this version does a little more intelligently is just cache, in a sense, the length of that string. And then we check I against n rather than the return value of some function again and again. Now, in real terms, if you were to run this program all day long on the string foo in both version 1 and version 2, you're probably not, certainly as a human, going to notice a difference. But when you start writing programs that take much larger inputs, doing things like this are much better designed, so to speak, certainly, than the first version. One, they just make more sense intellectually. And two, for larger inputs, they will, in fact, save you time and have your program running faster. So when we start talking about design, which we do in problem set 2, these are the kinds of thoughts you should start having. Focus, yes, on correctness of your code and getting it to compile, certainly, but also consider, can you do better once your code is actually working? Another question, I think, came up. Oh, OK. OK, other question. Good question. So this special value null, when does it work? It's used in the context of pointers. And so the foreshadow here is because we're saying that strings are, yes, arrays, but really an array is a pointer to a data type, which in this case is char star. Anytime you're talking about pointers, can you discuss null? And because strings are related to pointers, we check for null as the return value. And for those of you who didn't follow along with that thread, that's fine. It's coming in 2 weeks. Other questions? Is there a time when what? Oh, absolutely. So are there circumstances in which you would want, within the condition of a loop, to keep calling some function? Absolutely. I mean, silly example here, but if somehow the length of that string were changing, if maybe we were chopping off one character at a time for whatever purpose, absolutely would you want to keep calling that function or doing something else dynamically? Yeah?
Instead of having the if statement at the top, if you say s bracket I does not equal null, if I is less than 10.
S bracket I. OK, so could you check not string for the value null, but S bracket I? So short answer, yes, but the reason is perhaps subtle. So if you want to find the end of the string, you would, in fact, just keep checking S of I for null again and again and again. And that would help us find the end of the string. But the situation we're worried about is when getString doesn't return something like foo, but really returns nothing. That is, it doesn't even return a chunk of memory. It returns what conceptually is this, nothing. And so it returns, technically speaking, null. So what we're trying to avoid doing is even looking at any memory locations if they just don't exist. In other words, if in this very first line here, I instead just checked, well, let's make sure that the first character is not null. And if not, that implies that there's more. But the problem is if getString doesn't return anything, there is no 0th location that belongs to you. So you run the risk, again, of those seg faults or of touching memory that isn't yours. So that's why you sort of have to head it off with checking the string's value itself. OK, so let's take a look at how else this comes up. So in capitalize.c, we have a little program we whipped up that, quite simply, capitalizes letters. So the neat thing about this is that we can pull back into the conversation the issue of casting and subtracting characters from characters. And this time, I'm just trusting in C's representation of characters as ints and not even bothering with the explicit cast, because I know what the expected behavior is as of now. But take a look at how this integrates some of the stuff we looked at already. So here we just get a string. And it apparently seems that I'm not even checking now for null. Does this code run the risk of crashing? I don't have that line, if s not equal to null. Is that worrisome? Okay, I heard a couple yeses. Once we hear a no, I'll move on. Yeah.
No.
No, why not? So it turns out, no, it's not worrisome because we have a built-in sanity check here, but it's perhaps a little implicit. Yeah.
Wouldn't string length be 0?
Exactly. So the people who wrote string length presumably were smart and can detect if a string is of 0 length. That is, it looks like this. There's nothing actually there. So assuming that string length does return 0 when s itself is null, that is, there's no string there, well, then n gets initialized to 0, as does 0, which means how many times is the following loop going to execute? 0 times, so we're actually safe. So it's implicit. Is it better or worse? That's debatable, but it certainly does work. And this is perhaps a reasonable habit to get into. So long as you are aware of the errors that might occur and ward them off in this way, then your code is certainly at less risk of crashing. But now let's take a look at the conditions inside. It appears to be that no matter what, some character is getting printed. But in the first pair of lines here, what's happening in the case where the ith character of s is between little a and little z inclusive. So I'm clearly doing some math. And so what this has the effect of doing, because of the mathematics, the details of which I'd refer you back to, say, the ASCII chart that we looked at in week 0 and what numbers represent what characters here. If I go ahead and compile capitalize.c, notice that what we have is a program that when run just gives me a blinking prompt, and I might say this is a test exclamation point, and it does appear to capitalize everything without messing up, say, punctuation or changing what was already, like the capital T, an uppercase letter in the first place. So that integrates the ideas of loops iterating over strings as though they're arrays of chars, and also pulling back into the conversation casting, as it were, and also these conditions. So consider that sort of the culmination of several of those ideas. So how did I know that string length even existed? Well, it turns out that there are many more library functions available to you than, say, printf alone, string length being just one of them. Problem set 2, in fact, encourages you to make use of some of these library functions. If you click resources on the course's website, under the category C, I would dare say the best resource on this site is this one called C/C++ reference. It looks like this. For this class, you can largely ignore everything on the right because it's C++ specific, and we're focusing on C. And you can see I already pulled this thing up today. The second link here, standard C, string, and character. These are all the functions that you get for free with C that somehow relate to strings. Many of these, it's perhaps a bit premature to try using, but we do explicitly recommend a couple, such as A2I, isDigit, these little helper functions that are documented here. And you certainly should now have the savvy or brewing savvy to read this kind of documentation, figure out what kind of inputs a function takes, what kind of outputs it might produce, and thus how you might want to integrate that into your own program. And what's nice about this reference is that it often provides little code snippets to give you a sense of how it works. But by all means, ask questions of us. So do take advantage of that. And there's another one linked at the other URL there. So it turns out that though we just made mention of them explicitly this week, you've been seeing arrays and you've been seeing character arrays for quite some time. Several of you have asked why you need to type this at the start of your main program. Well, it turns out you don't have to. And many of your teaching fellows in section might have been taking the more casual approach of just writing main. Just writing main, open parenthesis, close parenthesis. Or writing void main, open parenthesis, close parenthesis. Or some other combination thereof. Compilers these days, like GCC, are pretty tolerant of which approach you can take. I've taken the approach of always being explicit and sort of presenting the scariness that was this function's declaration, because now, finally, it should make a bit more sense. It turns out that main, the function that gets called by default when you run your programs, okay, softball question, takes how many arguments? Okay, so 2. The first of which is an int. Typically, it's called argc for argument count, how many arguments were passed to your program. And then it appears to take what as its second argument? Okay, so I'm going to pretend that I heard an array of strings, aka an array of char stars, which for now are synonymous. So that's why we've been writing that notation there, because somehow or other, just as you can pass values to functions, well, main is a function, but who calls main? Well, it's really you, in a sense, that calls main by typing your program's name at the prompt. And it turns out if you type words after a.out or foo or whatever your program is called on the so-called command line, those words or numbers do get passed into your program by way of these arguments. So let's take a look. In argv1, we have the following behavior. So GCC of argv1 libcs50, run this thing. Nothing appears to happen except it appears to echo its own name. And actually, let me get out of my habit of specifying the path. All right, well, what if now I type foobar? Well, it looks like the program somehow knew what I typed, foobar baz. Well, if I just string these all together as one word, it seems to know that as well. So let's take a look at argv of 1. So this very short program is simply using all the syntax we've introduced thus far to iterate over all of the strings in argv, which because of those brackets is clearly an array. And what's it doing on each iteration? Well, it's iterating from 0 to argc, which we promised is the number of arguments passed. And then it's just printing each of them as a string, printing the ith string in the array. So not all that much magic. But the nice thing now is we can control the behavior, presumably, of programs by passing arguments to them at the command line. And problem set 2 has you do exactly that. In argv2, we go a little farther. Notice that there's a bit of recursive definition here. argv is, again, an array. But it's an array of what? Strings. But what are strings? Arrays of characters. So there's sort of like a two dimensions going on here. You have an array of strings, but which in turn are arrays themselves. So if we take a look at this code, notice that this time I'm again iterating over each of the arguments, the command line arguments. But then I have this nested loop, which has a different iterating variable, j. Notice that I'm iterating now from j up to n. But what's n? Well, it's the length of the ith argument. j++ on each iteration is my update. And then what am I doing here? Well, because these things are just arrays of arrays, you simply use the bracket notation twice. So if you want to touch something in the ith argument, that is the ith string, we'll just say argv bracket I. But if you then want to dive deeper and take the jth character of the ith string, you just do a second pair of square brackets and say j. So in memory, what's essentially happening here, and we'll come back to this when we talk about pointers, is if you have essentially an array of characters here, how best to depict this? What you essentially have is this might be FOO, and then immediately below that or next to that in memory might be foo, then bar, and so forth. But we're actually going to refine this picture when we get to pointers because it's not quite as pretty as a nice little grid. There's actually going to be arrows in our figures and discussion of addresses and pointers and such. But for now, that's just the idea. If you have an array of arrays, it's sort of like a big grid in memory, and you can access it with this double bracket notation. So why is that useful? Well, you will see quite soon in problem set 2. But a couple questions came up. Yeah?
When you say that the RV is specified number of inputs, that the in RV knows how many inputs you've given to me?
Uh-huh.
When you type those in, like when you type foo, bar, baz, you're separated by a space.
OK.
It seems to recognize each of those as a separate input.
Yes?
Does a space always do that? Or?
Excellent question, which I left implicit. So yes, to summarize, command line arguments are assumed to be any sequence of contiguous characters separated by white space, which just means I could type foo bar, and that gives me these arguments in argv. Or I can say bar, but that also just gives me those arguments. The computer, the operating system, will essentially throw away any unnecessary white space. But if for some reason you actually want to put a space in the word, well, that's not going to work. It's going to get passed in as multiple arguments. But if you enclose it in single or double quotes, then it actually gets passed in as one entity. But there's another anomaly here, right? What's the 0th string in argv, apparently? A.out. So that's actually a useful thing because in sort of this reflexive manner, your program can figure out what its own name is. But realize the real first command line argument then is at argv of 1, if and only if argc is big enough to suggest that there's something there. Okay? Yeah?
So two-dimensional arrays can have, I don't know, what would you call them, sub-arrays of different lengths?
Yes. So when you start talking about two-dimensional arrays, you can have what are called ragged arrays, where it's not a perfect grid, but this row might be this long, this row might be this long, and so forth. We'll actually come back to that with problem set 3 in the game of 15 when we focus on two-dimensional arrays even more. Okay. All right. So about that library. So CS50's library has source code that we did release for those more comfortable for now. We will come back in the future and look at the actual source code more closely. If you're curious to look at it, go on the bulletin board under announcements, and there's a URL for finding it. But these are all of the functions in CS50's library. And also defined in there are bool, as we promised, which we provided as a convenience, and string. But it's string that I at least want to show you. What I'm going to do is pull up via our website that library, which happens to be, and again, the URL is printed in the bulletin board. If I go here, releases, CS50, here's the header file, so to speak. And this is the file, again, that you include, sharp include at the top of your file. It's a little small, the font, but notice that roughly in the middle of the page here, there's this line that starts with typedef and then uses this keyword enum, which we'll come back to over time, which apparently declares a Boolean data type to have values either false or true, 0 or 1. And then there's this thing. So we said earlier that string is just char star. So that word typedef essentially allows you to define a type as a synonym for another. So that's all we've been doing, just to sort of hide that star from you for now. But we'll quickly reveal what that's all about in a week or two. Yeah?
Is the Boolean variable, is that just one bit or is it actually storing the true and false characters?
So good question. So what data type is an enum actually using? I believe by default it uses the machine's word size, which is an int in this case. So we're actually wasting 31 bits, but there's no way other than using a char to express a smaller value. And even if we use a char, we're wasting 7 bits. But for the machines today, it's not such a big deal. Okay? All right, so I put parenthetically up top there, memory leaks, which is to disclaim the fact that this library is not as robust as it could or should be, or rather the usage of it that we've been preaching isn't quite how you should be using these things. Thus far, you've been calling getString a lot in your programs. But what getString is really doing, if you look at the source code for this library, is it's dynamically allocating memory for that string. It's asking the operating system for a chunk of RAM. But how many of you in your programs thus far have ever been giving that RAM back to the operating system? Probably none of you. It turns out there is a keyword free, which frees the memory you've allocated, which ultimately you will need if you continue using CS50's library, because just as our library is asking the operating system for memory, when you're done with it, you better give it back, at least as a general principle. If you've ever run software on your Mac or PC that over time just seems to really, really slow things down, and if you're sort of savvy enough to pull up the task manager or the equivalent on your computer, and you see that, my God, like AOL Instant Messenger is taking up 60 megabytes. Well, that sounds excessive for an instant messaging program. Odds are it's because that whoever wrote that version of the instant messaging software had some bug, made some mistake, and over time might have kept asking the OS for more memory upon maybe receipt of every instant message. But if that programmer never ever gave that memory back, his software has what's known as a memory leak. And the idea is the longer your programs run and the more memory they ask for but never give back, the more space that your program, by way of that conceptual rectangle, takes up in the computer. And you only have a finite amount of RAM before other things start happening, virtual memory, disk swapping, terms like that. The effect, though, in real terms, is to slow your computer down. And what's typically the fix? Restart, right? Because that kills the program, frees up memory, and the whole big mistake can happen again the next time. Yeah, question? Is there any way to fix that without restarting? Short answer, it depends. So operating systems have gotten a bit better, perhaps, at reclaiming memory once they realize the program is dead. So if you just kill the program, sometimes it does reclaim. Even that isn't necessarily reliable because programs will load drivers into memory, and there's things that you can't just quit or force quit these days. So the most robust solution is, in fact, to reboot. Better is to upgrade to software that doesn't contain those bugs. And this is a problem to this day. I saw a thread recently about the current number of memory leaks in like Firefox, which is still a problem for these programs that are written in C, C++, and these languages that don't have, as a sneak preview, what's called garbage collection. Long story short, Java and other more recent languages take care of all of this memory management for you. One of the ideas being that you can't trust the programmer to do this correctly himself. right? If in 2007 the makers of one of the most popular software products are still screwing up, maybe we need to give them languages to facilitate writing software, but you do have that in other languages. But for us, it's kind of nice to play at that lowest level and see what's going on. So as promised, we will come back in our secure coding lecture to issues like buffer overflows, when we said yesterday on Wednesday that a buffer is usually just an array of characters. But for today, we're going to conclude on a note of cryptography and set the stage for your problem set 2. So problem set 2 is ultimately meant to give you a bit more savvy, a bit more comfort with actual programming and some of the stuff we've looked at over the past week. But it's meant to do it in a sort of sexy, trendy context, which is cryptography. And sexy, trendy is sort of one way to say it, but our cryptography goes back to many, many, many years ago. And this is sort of a silly way of introducing this, but recall that we put this on the board just the other day, which was a ciphertext. It's encrypted text that represented what? Be sure. All right. That's a boring answer yet. Be sure to drink your Ovaltine. So that came again from this movie, A Christmas Story, and it was encrypted with a cipher called what, did we say? ROT13, which probably isn't what they did in the movie, because I don't think Ralphie ever showed you what was on the cereal box. But ROT13 is a specific instance of what's generally known as the, sneak preview of Matthew McConaughey there, is a special case of what's generally known as the Caesar cipher. So the Caesar cipher is simply an algorithm that takes the input characters, say A through Z, and rotates them by some number of characters. Let me pull up one thing here, which we'll come back to in a second. So let's actually go ahead to Matthew McConaughey, and we'll give the whirlwind tour of cryptography in the real world. So this is a screenshot from the semi-popular film U-571 starring Matthew McConaughey. I think he was on the American side. And the goal of Matthew McConaughey in this movie was to capture an Enigma machine from some German U-boats. What's an Enigma machine? Yes, that. What was it? Well, the Caesar cipher is probably not the best thing to be encrypting World War II messages in, right? Because if anyone has a piece of paper and pencil in a few seconds, they can guess which of the 26 letters you chose or numbers you chose to rotate your characters. And look to Wikipedia for the backstory here, but the reason it's called the Caesar cipher is supposedly, 2,000 some odd years ago, Caesar used a Caesar cipher, though he didn't probably call it that at the time, to encrypt his messages to his generals. And granted, we're sort of predisposed to thinking about things from the lens that we're taught to use these days. I still frankly find the legend hard to believe that Caesar just took his messages and flipped a few characters and actually entrusted that, because I would hope 2,000 years ago people might have had at least a bit of common sense to know how to tackle those problems. But for us, we'll accept the legend as fact. Caesar used this cipher. The Enigma machine is a hardware implementation of a cipher, which just means that by a series of gears and levers and complicated machinery, you type in some input and it produces some output, which is scrambled, but scrambled in a much harder way to descramble because it leverages all these complicated gears and levers. So Matthew McConaughey really wanted to save this machine and take it off of some German sub. Why? Right, so he could descramble so that he could decrypt German messages. The problem with systems like these is that they entrust the secrecy of your messages to what effectively are keys, things that if you know the value of or you have possession of, you can unlock messages. And so that's an arguable weakness, because all it takes to compromise, say, the German secret messages is theft of the very machine that they're using. And as I recall, that was pretty much what the 2-hour movie was about, and getting this machine. So how does this fit into a more general framework? So cryptography is the art, the science of concealing information, typically through algorithmic processes, doing it mathematically or generally doing it in a manner that can be reproduced again and again. Secret key cryptography, aka symmetric key cryptography, describes exactly the Caesar cipher and even the Enigma machine, whereby if you take some plain text, that is some original message that you want to encrypt, and you pass it through some kind of machine or function, algorithm, using as input some secret, like a number, like 1 through 26, or a secret, like the gears and levers that to collectively implement the Enigma machine, what pops out of that process is so-called ciphertext, the scrambled message that ideally to the human eye looks confusing. It doesn't look like an actual message. This kind of approach, though, is symmetric in that by having possession of that same machine or knowing that same secret number 1 to 26, what can you do? You can presumably reverse the process, and you can decrypt the ciphertext back into plain text, and thus using the same key symmetrically to both encrypt and decrypt. So that's an example of secret keys or symmetric cryptography. Caesar was an example of that. Just to make it more clear pictorially what's going on and to formalize the Caesar cipher, if we really wanted to put Caesar into mathematical terms, what we have is a formula like this up here. C is generally going to represent ciphertext, P is generally going to represent plain text, and K are key. So what this is implying is that generally for the Caesar cipher, you take the ith character of your string, call it P sub I, add the key, and then why are we doing mod 26 apparently? Exactly, because modulo, and this is a really neat, if subtle, feature of modular arithmetic, or the mod operator in C, is that it allows you to wrap around, both conceptually and literally. And so for a problem like Caesar cipher, where you do want to wrap around the alphabet from, say, Z back to A, the operator that allows you to do that is mod. And you might have to do a bit of trickery if you're dealing with ASCII, because you don't want to wrap around from 65, 66, all the way up back to 0 or 1, because then you're going to get garbage characters on the screen. But certainly the principle does apply. And problem set 2 leaves it to you to figure out exactly how to do that in C. Well, Caesar's all fine and good, but what is, again, to be clear, a weakness of it? It's really easy to decrypt, right? You can guess the keys. Better yet, you can try all possible keys. Even doing it by paper pencil, odds are you could try all 26 possible keys and eventually realize what the key was, because the plain text would eventually jump out at you. Well, the so-called Vigenère cipher, named after a Frenchman, Vigenère, is similar in spirit to Caesar, but uses larger keys, so to speak. So whereas Caesar simply uses a number to rotate characters in a text, Vigenère uses a whole word to rotate the letters in a text, whereby each character in the word itself represents a number. So if in your keyword, according to Vigenère, your keyword was just AAA, that would represent the keys 000. If instead your key was ABC, your keyword was ABC, well, that would effectively represent the keys 0, 1, 2. The idea then is that you rotate each letter in your plain text by a different letter of your key. But obviously, if your plain text is longer than your key, well, you don't want to just stop. Otherwise, you'll have encrypted just the first 3 letters of your plain text. But rather, you repeat the key again and again, as many times as it takes to repeat this process. So suppose that our plain text here was hello world. And suppose that our key was foobar in F-O-O-B-A-R, no spaces. It quite literally is a key word. Well, the effect of that, if we apply Vigenère cipher, is to add the value of F to H. So we have A, B, C, D, E, F. So that's 6. So we're essentially rotating H by 6 characters. So H, I, J, K, L, M, N. Oh, what did we do wrong? H, I, J, K, L, M, N. I'm going to have to double check our encoding online, make sure we're consistent in the spec. In any case, you take the letter represented by, A, B. Oh, right, A is 0, so I'm counting wrong. So we do, in fact, rotate hello by the numeric equivalence of that key. And we simply take a mapping of A is 0, B is 1, all the way down to Z is 25. You have to agree upon an encoding, and problem set 2 tasks you with just using precisely that simple encoding. But again, because hello world is longer than our key, we just repeat it again and again. But take care to note, what do we not bother rotating with Vigenère according to this definition? Okay, so we don't rotate the comma, the punctuation, the spacing, and so forth. So similarly, well, problem set 2, just have you scramble the alphabetical characters, nothing numeric or punctuation related. Okay, so is this better? How would you describe the security of Vigenère, say in terms of the size of the keys that it now allows? Well, it's more secure clearly if you use longer keys, because it's just harder to guess, right? So that has the effect of encrypting things more thoroughly. But what's a downside, perhaps, of using longer and longer keys? Sorry? So it's harder to remember, right? Just like long passwords are a pain to remember, long keys are more difficult, presumably, to remember. Well, you can write it down, but that's sort of contrary to the spirit of hiding information in the first place. So assuming a reasonably length key of size n, So if the key size is n, how many possible keys might Vigenère have at his disposal? Just to make clear the power of this versus Caesar. Yeah, it's 26 to the n possible keys. The key space, so to speak, is 26 to the n. So you start taking n equals 1, and the thing devolves into Caesar's cipher. You have 26 possible keys. But very quickly, exponentially so, does your so-called key space grow as the length of your key grows itself. And even for reasonably sized keys, you have a huge key space, which means what for the bad guys, the so-called cryptanalysts? Yeah, it takes much longer to figure out what the key might be if your approach is that so-called brute force approach of trying all possible keys. So again, with just a slightly more sophisticated design, are we able to enhance the security of our plain text in terms of its ciphertext by just growing the key. And you'll see in problem set 2 exactly how you might go about implementing this. And the formula in general is captured above here, but the idea is essentially the same. But you're rotating the plain text by perhaps different characters in your key. Well, fortunately, the real world doesn't use Caesar. And the real world probably doesn't tend to use Vigenère because there are more sophisticated approaches to cryptography. To give you a sense, a popular one is called DES. And DES works like that, which is the picture on the right. And it essentially involves using a Feistel function and running your input, which is essentially lots of bits, through a function again and again and again. And every time you do it, you sort of move these bits over here and these bits over there. And you just repeat this process, usually, I think, 16 or 16 times total. Out of that pops something that looks really, really scrambled. But because of the way this thing is designed mathematically, you can reverse the process in the other direction, which makes it another instance of a secret key cipher. It uses 56-bit keys typically. Using that many bits, not just 26 characters, but 56 total bits, turns out that the key space for DES is what? Like 72 quadrillion possible keys. That's going to take a typical program a long time to guess all of those keys. Turns out DES has, in fact, been cracked in the sense that folks have thrown very good algorithms, very good code, and, say, supercomputers, multiple CPUs at these problems, and have been able to figure out even stuff that's encrypted with DES. The hacker edition of problem set 2 actually puts you to task with a variant of the DES algorithm in the terms of password protection. But more commonly used today than just something like DES alone, which for the curious has been replaced with a more modern algorithm usually known as AES, Advanced Encryption Standard, is the use in the real world of what's called public key cryptography, or rather asymmetric key cryptography. The idea here is essentially as follows. When you're using secret key crypto and Alice wants to send a secret message to Bob, what must both Alice and Bob know for this process to work? They need to know that the secret key is used, or whatever key they're using. Well, the problem here is that what if Alice has never met Bob? Or what if Alice and Bob just didn't remember to agree in advance on some secret key? Well, you have sort of a chicken and the egg problem, right? Alice can't talk to Bob securely until she tells Bob what password she's going to use, but she can't tell Bob the password securely because he doesn't yet know the password. Right? So of course Alice could just whisper into Bob's ear or call him up and tell him the password, but then at that point she might as well just tell him the message in the first place. Right? So you have, again, this chicken and the egg problem that public key crypto aspires to redress. In the world of public key cryptography, which today's browsers and maybe even ATM machines and other popular pieces of hardware use, you have an inherent asymmetry. As a result of a fairly complicated set of mathematics, each user in that story, Alice and Bob, have what's called a public key and a private key. And there's this inherent mathematical relationship between the two such that it's perfectly safe, given certain assumptions, for Alice to publish on her web page, to yell to the world, to send out in the footers of her emails her so-called public key. And her public key essentially looks like a really big number. This, in fact, is Ron Rivest's public key, who's a professor over at MIT and is one of the authors of RSA, which is an algorithm you might have heard. I just looked this up in MIT's directory. And so Ron can essentially publish this on his web page and say to the world, anytime you want to send me a secret message, encrypt your message with my public key. What Ron Rivest can then do, using the corresponding private key that corresponds to his public key, is, because of this mathematics, decrypt any message sent to him with that was encrypted with his public key. So similarly can Bob have his own public-private key pair. And if Alice wants to talk to Bob, she downloads his public key from, say, his website, uses it to encrypt a secret message, and then sends from Alice to Bob her encrypted message. Bob can then decrypt that message with his private key. And one of the most common instances of public key cryptography is what's known as RSA, which is in use even in a lot of your browsers. If you go to Internet Explorer's, I think, Help menu and then About IE, somewhere there in the credits, they'll mention RSA. RSA, mathematically, and this is just a teaser of what you can get in courses like CS120, essentially treats a public key and a private key as just a pair of numbers, generally called E and N. N is just the result of picking a really big prime number and another really big prime number, multiplying them together, and getting an even bigger number back. The idea conceptually being this thing is so huge it would take practically forever to guess what those prime factors were, to figure them out by brute force. But once you have this mathematical relationship between n and then these other two values, e and d, encrypting a message with RSA really just boils down to some mathematics. You take your plain text, p, and maybe take it as the ASCII equivalent for each character, so the number 65, 66. You raise it to the power e, mod n, and that gives you back the encrypted version of that character. And reversing that process simply involves raising the ciphertext character to the d power. I'll put this up for those of you more comfortable, interested in these mathematics, but otherwise we'll leave you on this note and task you with problem set 2 for next week. Good luck. And some of the teaching fellows have assignments to pass back. If you see your teaching fellow here, otherwise you'll hear from them via email.